Hello there, Mr. Sutton here, bringing you the Algebra 2 4-2 lesson on adding, subtracting, and multiplying polynomials. So if you're taking this as the non-honors course, this is a 3-part lesson. For the honors, this will be a 2-parter. Specifically, we will be adding and subtracting polynomials, as the title suggests, and also multiplying polynomials. And we'll also look at some special product patterns and review some that you've seen in the past. And finally, something of a new topic, we're going to be using something called Pascal's triangle to expand binomials, especially ones that are bigger than second power. So we're just going to dive right into it and try simplifying this sum here of two polynomials. I think you might already know everything you need to do this, but let's just check. Pause the video and see if you can simplify this expression. All right, so let's see how that went. So now simplifying in this context means we can't have any parentheses, and we also don't want any like terms left at the end. So let's get rid of the parentheses first. Now each of these parentheses has an invisible 1 on the outside of it. So to get rid of the parentheses, you're essentially just distributing an invisible 1. So that changes absolutely nothing in our first parentheses and absolutely nothing in our second parentheses. So you kind of just lose those for free, but again, what's really happening is you're multiplying by an invisible 1. All right, now at this point we have some like terms to combine. Those are terms that have both the same variable and exponents, so they have to have both. And as an optional step, you could, if you wanted to, rewrite this so that you had the like terms next to each other. That might make it a little bit easier to look at, especially when you have this many terms floating around. Alternatively, you can just find the ones that have the same type of term and add those together. So we've got 3x cubed, and over here there's a 1x cubed. That's going to be 4x cubed. Next up, 2x squared and negative 10x squared adds up to negative 8x squared. And then we have a negative x, and there's no other x's here, so that one just gets rewritten. And then finally, negative 7 plus 8 is going to give us a positive 1. And that's it. There's no more like terms that we can combine. Now, another way that you may have seen folks do this is if you wanted to, you could rewrite this vertically so that you had the like terms underneath the other like terms, kind of like when we were doing systems of equations. That is another way to go about this, but you don't have to do it that way. All right, so let's move on to the next one now. So for this next example, we're going to be simplifying a difference of two polynomials. It's kind of the same idea as a sum, only with subtraction, which does add a little bit of a curveball in the beginning. Pause the video and see if you can spot what you need to do here. All right, so for the first parentheses, we again have an invisible 1 out there. That changes nothing, so we still have 2z squared plus 3z. For the next one, however, we have an invisible negative 1 out in front, which means I need to distribute a negative 1 to everything in this next parentheses. So that's going to be negative 3z squared, and then minus z, and then minus minus is going to be a plus 4. So that was really the main difference between these two problems. And then combining like terms, 2z squared minus 3z squared is going to be a negative 1z squared, and we don't have to write the 1 there if we don't want. And then we have 3z minus z, that's going to be a plus 2z. And then finally, the only thing left here is 4. Now, one thing that might be helpful to also do when you're combining like terms is perhaps after you combine two of them, cross off the ones you've combined. So, for example, after I added these z squareds together, maybe I could have crossed them off just to have one less thing to keep track of. Again, totally optional, but these are some nice organizational things you can do to decrease the chance that you're going to lose something. So we're going to do one more example with adding and subtracting. If you're taking this as the Algebra 2 college prep non-honors sort of lesson, this will be one more for this part of the lesson. If you're doing the honors version, then you can just zoom ahead to the next example. So here's just another one to try out. Pause the video and give it a shot. All right, so just like before, we can lose that first parentheses for free because there's an invisible 1 out in front. And just like the last problem, we have an invisible negative 1. There's just 4 terms now instead of 3. So this is just a bigger, badder version of the problem that we just saw. So we have minus 2x cubed minus 6x squared plus x minus 1. And then the 8x cubed and negative 2x cubed gives us 6x cubed. Negative 3x squared minus 6x squared, that's going to be negative 9x squared. Negative 2x and x is going to be negative 1x. And then 9 minus 1 gives us a plus 8, and that's all we need for this one. So if you're taking this as the non-honors version of the lesson, then this is the end of part 1 for you. Feel free to pause the video, do some practice on adding and subtracting polynomials, and then join us for the next part where we talk about multiplying. So welcome back if you're rejoining us from the non-honors CP course. If you're doing the honors version of this lesson, then you never left, so welcome back anyway. So for this one, we're going to be multiplying out two of these polynomials. That's what these parentheses mean. The parentheses mean multiply if there's nothing in between them. So how do we go about doing this? Well, the basic idea is we're going to have to use distributive property. We're going to have to distribute everything in the first parentheses to everything in the second parentheses. Now, if you want to write all this out exactly what's happening, we've basically got negative x squared times x minus 3. We've got a plus 2x times x minus 3, so each of these things getting distributed, and then 4 times x minus 3. So we have to do all these multiplications. So pause the video, see if you can take this the rest of the way, multiply, combine like terms, all that sort of stuff. Alright, so we're going to use distributive again. Now we have all these little mini distributive sort of situations. So negative x squared times x is negative x cubed. Then we have negative x squared times negative 3 is positive 3x squared. 2x times x will be a positive 2x squared. 2x times negative 3 is negative 6x. 4 times x, that'll be 4x. And 4 times negative 3 gives us negative 12. Just combining like terms here, we have only one of these x cubed, so just rewrite that. And then we have a 3 and a 2x squared. That adds up to 5x squared. Negative 6x plus 4x is negative 2x, and then we have this negative 12 that's along for the ride. So this is kind of the long way of writing it all out, and you can certainly do this every time. You're not going to miss anything if you do it this way. One way you can sort of shortcut all this writing it out if you want is to draw little kind of lines connecting the things you're going to multiply. So for example, I could do x squared to the x, x squared to the 3, oops, did a little bit more than I wanted there, 2x to x and 2x to 3, and then the 4 is also getting some lines in there. So this is another way to kind of show this. It can get a little bit messy as you get more and more of these things being multiplied out, but that's certainly an option. Here's another multiplying problem. Pause the video and try this one out. Alright, so using kind of the long distributive approach, I've got y times this whole second parentheses, and I've got a plus 5 times this whole second parentheses. Again, don't need to write all this out if you just do like the little lines connecting things, but you're less likely to miss something if you do it this way. So distributing all that out, we've got 3y cubed minus 2y squared plus 2y. And then for the other one, we have, let's see, 5 times 3y squared is 15y. 5 times negative 2y is negative 10y. And then 5 times 2 is 10. 3y squared, there's only one of those y cubes. I should have said y cubed in the first place, so we're just going to keep that the way it is. Here's a squared, though. Negative 2y squared and 15y squared is going to be 13y squared. And then 2y minus 10y is negative 8y. And then finally we have just a 10 there. So if you're doing the honors version of this course, this is actually the end of part 1 for you. You can pause the video and do some practice on adding, subtracting, and multiplying polynomials. If you're doing the CP non-honors of the course, then you've still got another problem to go in this part 2 that you're in, so stay tuned for that problem. So whether you're rejoining us from the honors course, beginning part 2, or still continuing part 2 from the CP course, here's our next problem. This time around, we're not multiplying two polynomials we've upped this to 3 polynomials. And this is a little bit of a game changer. When you had 2 polynomials, you just multiplied it all out, combined like terms, and then that was the end of it. But this one, if you have 3 of these, you can't multiply all 3 of these together immediately. The trick on these is actually going to be to first multiply 2 of them together, simplify that, and then whatever you get from simplifying that, multiply it by whatever's left over. If you try to do everything all at once, it's going to be a mess and you're going to leave things out. So I would pause the video, try this strategy out, and then let's see where we end up. Alright, so multiplying 2 of the factors together. Now it doesn't really matter which 2 factors you pick, but I typically pick the first 2. I just like to go from left to right unless there's a really good reason not to. So we've got x times x, that'll be x squared. X times 4 is 4x, and negative 1 times x is a negative 1x. 4x and negative 1x gives me a 3x in the middle, so I'm kind of simplifying in my head as I go, otherwise it's going to be a lot of writing things out. And then negative 1 times 4 is giving me negative 4. And I still have this x plus 5 left over from before. So now let me write it out so that I'm distributing everything in this first parentheses by this last one. This is going to be kind of like example 3. So we have x squared times x plus 5. 3x times x plus 5, and negative 4 times x plus 5. So we have x squared times x is x cubed. This will be 5x squared. Next up, 3x and x gives me 3x squared. 3x and 5 is 15x. And then we have negative 4x and negative 20. X cubed is the only cubed there. We have 5 and 3x squared gives me 8x squared. 15x minus 4x is 11x, and then finally we have this negative 20. And that's it. So again, multiply 2 of them together, simplify, then multiply by what's left over. If you were doing the CP version of this course, then this is the end of part 2 for you. You can pause the video and do some practice with polynomial multiplication. If you're doing the honors course, then we've only just begun. Let's take a look at some shortcuts on the next problem. So welcome back. If you're rejoining us from the CP version of the course, this is the beginning of part 3, or we're just continuing part 2 for the honors. So for these next couple problems, they're asking us to find the product using a shortcut or Pascal's triangle, which we haven't really gone over yet. But if you just have 2 things being multiplied together and you have the same stuff, like we have a 4n and a 5 here, there's a couple shortcuts we can use. And we've actually seen these before in this course, but this is just kind of a little review. So if you have, this is called conjugates here. If you have something plus something and the same something minus the same something, this is basically a plus b and a minus b. We've seen that the shortcut for that is basically just a squared minus b squared. Essentially square the 2 things and stick a minus between them. So pause the video and let's just review using that shortcut on this one. Alright, so let's see how that went. 4n squared is going to be 16n squared, and then 5 squared is 25, and it's always a minus on this shortcut, so minus 25. And that's it. There was no need to distribute things out. If you had, you would have had like a negative 20n and a positive 20n in the middle that you could have canceled. This just saves us a little step. Alright, so moving on now to the next one. We have 9y minus 2 quantities squared. This is a related shortcut also involving some squaring of things. Basically, this is 9y minus 2 times another 9y minus 2. We still have sort of repeated things going on. The shortcut for this situation is if you have a plus b or a minus b, it's going to be a squared and then whatever the sign was in the middle with a 2ab, and this is always going to be a plus b squared out here. So basically square the first thing, multiply them together and double it for the middle term, and square the last thing. Pause the video and review using this shortcut. Alright, so on this one we have 9y squared is going to give me 81y squared. Multiplying these together and doubling it, so this would be negative 18 if we multiply them, and doubling that would give me negative 36y. And then finally 4 is going to be what we get when we square 2. So this just saves us the trouble of writing the parentheses twice and foiling distributing this out. This was also kind of the reverse version of the shortcut we were using when we were using completing the square. So this one's kind of important for multiplying and going the other direction as well. Now on that last example where we had a squared plus 2ab plus b squared, you might wonder, are there other shortcuts like that with a's and b's that I can just quickly, expand something that's being raised to some power without having to write everything out and multiply everything out? And it turns out there's a way to generate as many of those shortcuts as you want, called Pascal's triangle. So Pascal's triangle is basically just a system for generating coefficients in the shortcut formulas if you have an a plus b to some power. So just looking back at our last example here, we had 1a squared plus 2ab plus 1b squared. Where did the 1, the 2, and the 1 come from? We're about to find out. So Pascal's triangle, we begin this by just putting, we have different rows of the triangle. The first row is just going to have a 1 in it. And every row thereafter, from row 1 to row infinity, whatever, is going to have a 1 on the outside of the triangle. So here we've got a 1 and a 1, which seems kind of boring. So how does this get changed up? Well, on the very next row, row 2, we're going to see this. So we still have a 1 on the outside here, but now these inner sort of entries are going to be the sum of the two numbers that are above them. So this one here is going to be 1 plus 1, which is 2. And then we have a 1 on the end of the triangle. And then just to go one more row here, we've got 1, and then 1 plus 2 is 3, and then 2 plus 1 is 3 again, and then we have a 1. And we could keep going. But the real question is, why are we doing this? What does this get us? So this is, again, a way of expanding something where we have a plus b to some exponent. This n here is really corresponding to the row number in Pascal's triangle. So this row 1 is telling us how to expand a plus b to the 1 power. And the way to do that is we're going to have 1 and then an ab expression plus 1 and another ab expression. Now these ab expressions, a and b, both have exponents on them. The beginning exponent is always going to be whatever the row was, the highest exponent you can possibly have. And then the b exponent is going to be the lowest you can have, which is always going to be 0 to start with. So our first term is going to be 1, a to the first power, b to the 0 power. And then as you move one step to the right, the a exponent goes down by 1, the b exponent goes up by 1. So our next term is going to be 1 because of this one right here. And now this a to the 1 goes down to an a to the 0, and b to the 0 goes up to b to the 1. Now this is going to take some getting used to. A goes down, b goes up. It's a pattern. We're going to see this over and over again. But you might be wondering, well, what does this all actually mean? So if we take care of these ones that we don't really care about, this is really just a times, well, b to the 0 is 1. So this is really just a plus, and then this is just b over here, right? Because a to the 0 is 1, and b to the 1 is b. This is just a plus b. Is it a shocker that if you raise a plus b to the first power, you get a plus b? No, not so much. And we didn't need Pascal's triangle to do it either. I just wanted to start at kind of the lowest level to show you that this actually does work for literally everything in this situation. And also to kind of prove that it works by showing you it gets us results that we could get with other methods. So let's move on to row 2. This is a plus b to the second power. So our first coefficient is 1. This is going to be 1, a to the, now it's going to be second power, b to the 0. Our next one is going to be a 2, and we're going to have an a to the first, b to the 1. And then we're going to have a 1, a to the 0, b to the second. This is really just a squared plus 2ab plus b squared, which is exactly the shortcut formula we used when we did a plus b quantity squared. So this is one that we've already got in our bag, but Pascal's triangle gets it, and this is kind of showing that this triangle works for everything. So let's go one more row here, row 3. So this is a plus b to the third. So now we're going to have 1 a to the third b to the 0, or just a to the third. We don't have to keep writing this b to the 0 since we know it's going to be 1. Next, we've got a 3 a squared b to the first, or just b, plus a 3 a to the first, which is just a, and then b to the second. And finally, this is going to be 1 a to the 0, which we don't really need to write, b cubed. So this here is the shortcut formula for a plus b cubed. Now, you could memorize this formula. It's not too tough to memorize, or you can just regenerate it every time using Pascal's triangle. And we could keep going with this triangle, and we will. There's a few more rows we're going to see. But first, I'd like to just give you a problem to try this out on. We're going to do one more problem involving Pascal's triangle. This is an a plus b to the exponent sort of situation that's higher than 2, so it definitely warrants Pascal's triangle. So pause the video and see if you can at least figure out up to row 5 of Pascal's triangle. And if you're feeling really confident, feel free to use that to generate the shortcut formula and finish this thing out. Okay, so let's at least get row 5 here. So here was row 3 from before. For row 4 now, we can't go right from row 3 to row 5. We need to go through row 4 first. We've got a 1. 1 plus 3 gives us a 4. And then 3 and 3 is 6. 3 and 1 is 4. And we have a 1 right here. Now, row 5, this is the one we actually need for this problem. We still have a 1 on the outside. And now we're going to have a 5. 4 plus 6 is 10. We've got another 10 here. A 5 and a 1. So we're going to use this to generate a shortcut formula to deal with this situation. So this is going to be 1 a to the 5th b to the 0 plus 5 a to the 4th b to the 1st plus 10 a to the 3rd b squared plus another 10. This time we're going to have a squared b to the 3rd plus 5 a to the 1st b to the 4th, and then we have a plus 1 b to the 5th. So now we just have to plug in a and b. A in this case is just x. B is negative 2. Again, the sign has to go with it. So we've got x to the 5th. Now we're going to have 5 times x to the 4th times negative 2. And 10 x cubed negative 2 squared, followed by 10 x squared negative 2 cubed. 5 x and then negative 2 to the 4th, and then finally we have negative 2 to the 5th. Evaluating all of these, x to the 5th is just x to the 5th, so that one was easy. Here we have 5x to the 4th times negative 2, so negative 10x to the 4th. After that, negative 2 squared is 4. 4 times 10 is 40, so this is 40x cubed. And then we have negative 2 cubed, that's negative 8. So that's going to be negative 80 then with that 10 in there, and we have an x squared to go with that. And then let's see here, negative 2 to the 4th is 16. 5 times 16 is 80, so this is 80x. And then finally, negative 2 to the 5th is negative 32. So that's going to be it for this lesson. Thanks for putting the try in Pascal's triangle. Until next time, Mr. Sutton signing off.